Welcome to our video presentation that will be substituting the poster session for IAP. In this video, we will be discussing the runoff road prevention and detection system. Our team, going from left to right, consists of Juan Cabrera, José Barreras, Ramos, Gustavo Marrero, and Misrael García. Hope you enjoy.
The following block diagram represents how we are aiming to model the machine learning aspect of the project. To the left, we have the different components of our training set, which consists of the recorded accident data, simulated accident data, and weather data. The simulated accident data will come from real trials of a vehicle on campus to test the employee sensors. Moving to the right, the data preprocessing section will convert our raw data into a structured format that can be adequately processed by a machine learning algorithm. Next, we have the machine learning algorithm to be used, which is a neural network. The reason for choosing a neural network is that we expect a complicated decision boundary in our training dataset. Otherwise, if necessary, logistic regression can also be tested if the decision boundary doesn't appear to be too complex. Lastly, we have our runoff road prediction model, which will be fed the real-time data from the sensors, which will provide the vehicle's speed and the humidity of the environment that can be translated into the approximate coefficient of friction of the road. The output of the model will give us the probability that a runoff road accident happened.
For our first and most important sensor, we are using the MaxSonar EZ3 sonar rangefinder, which is an ultrasonic sensor that has a max range of 25 feet. Thanks to this, its small footprint and low power consumption, it was a comfortable choice for the beginning of our project. In terms of the setup of these sensors, we use them to constantly read the distance between them and the pavement. Now you may ask, how do we measure the velocity? It's simple. We place a sensor, let's say S1, a certain distance from the second sensor, let's say S2. It will look something like this. The way this works is after S1 trips due to a car passing, a signal will be sent to the MSP to begin a counter. After that, it waits for the S2 to be tripped. When that happens, the total time will be taken, and with some simple calculations, we can determine the velocity of the vehicle entering the curve. So far, they have worked well for the job they were chosen for, but the sensitivity of the sensors is creating a problem in which it reads a single car multiple times. This is not a big issue, and we already know how it can be fixed. Further testing is needed to fine-tune the readings. Now, to see how the MSP handles the information that is being sent, I will leave you with Juan Cabrera.
To acquire, process, and later relay all sensor readings, an MSP 430G2553 microcontroller is being used. This microcontroller, along with the ultrasonic rangefinders and XP wireless radio modules, compose our most basic prototype for a module capable of calculating a vehicle's velocity and communicating it to a remote server. Firstly, the sensor readings are acquired through samples of an analog to digital converter. Once acquired, these values are processed and checked in case they indicate that a vehicle has been detected. If one has been detected, then its velocity is quickly calculated, and a UART module within the MSP 430 is used to communicate the resulting value to an XP radio module, which in turn communicates the same value wirelessly to the server. Once the value has reached the server, it can be further processed to determine if any action needs to be taken.
We're going to implement the humidity sensor because we know that when rains or a vehicle passes with water or other liquid, it can drop them. Dropping liquids at the road can change the coefficient of friction at normal conditions. With this sensor, we could measure the humidity and calculate a new coefficient of friction, then calculate the new velocity and notify the driver that the velocity limit of the curve has changed, so he can reduce the velocity and he can pass the curve safely. These are some of the sensors we're looking at that we can implement at our project. We want to be able to identify a vehicle for two main reasons. First, this will be used to check if a vehicle enters and exits the curve, or even if it stops at the middle of the curve. We don't want to send a warning to authorities if the person suddenly stops for any reason. Second reason is that by identifying the vehicle, we could send a warning to a person and alert them there is a risky curve ahead, so that the person can take precautions and avoid a fatal accident. For this, our solution was to use a camera connected to a microcomputer such as a Raspberry Pi, so that it could use optical character recognition algorithm in real time. The Raspberry Pi seems like a good option since it's basically a computer of the size of a credit card, and because it's really cheap. To identify a vehicle and alert the driver that he or she is near a dangerous curve, we will use a license plate, since it's unique for every vehicle. In addition, that this will also help us know if a specific car entered and exited the curve without any problem, or if we should alert the authorities. The code recognizes the license plate, is programmed in Python, and is always running on the Raspberry Pi. We use Python libraries created to help with the task of character recognition from images and videos. In our case, we use OpenALPR with Misrael OCR engine with OpenCV libraries.